y, which of course you really have no control over. They're just what they are. But then it's also a function of these two parameters, which are the intercept and the slope, alpha and beta. And so to get this formula for beta, what we're doing is we're just taking this objective function, we're differentiating with respect to alpha, differentiating with respect to beta, setting those derivatives equal to 0, and going through the solution. So it's just like we do when we're trying to solve for like the profit maximizing level of production or the socially efficient level of production, something like that. So that's where you get this formula for beta. And so if you want to, you can kind of go down that route. But you can also basically take what I've given you here, which is that so what you have is that yi is equal to alpha plus beta xi plus ei, and you have that as well. And so you can solve for alpha in terms of x bar, y bar, which are the sample means, and the covariance of x and y and the variance of x. So what I want you to do in the group is sort of either so basically either solve this maximization or rather this minimization problem, and then tell me what alpha would be in terms of these four quantities. So the sample mean, sample variance, sample covariance, or sorry, sample mean of x, sample mean of y, sample covariance, and the sample variance of x. Or if you want to, you can kind of just work with formulas and the fact I gave you over there and solve for alpha in those terms alternatively. But either way, your goal is to, like I already gave you what the solution for beta is. I just want you guys to help with the solution for the intercept term, which is alpha. So I'll give you about like 5 or 6 minutes to work on that. Let me also say, so if you've like taken econometrics and you know some shortcuts about like properties of the regression line, that's totally fine. You can feel free to use those in your explanation for how you got the answer. Oh, sure. So I'll give you another hint also, which is that the mean of E bar, or the mean of EI, which is E bar, that's gonna be 0 in the optimal solution. So if you want to use that too, you can feel free to leverage it. Okay, so I'm going to choose some groups, and you guys, I mean, you can pass if you don't feel like you have an answer, but if you answer correctly, then you get more points. I guess I'll also post like how many points each group has in total, just so you have a sense of where your standing is. So group 5, did you guys come up with a solution for what alpha will be in terms of these 4 quantities? No. Okay. Okay. Is there? Okay. Let me try a different way. Is there a group that would like to volunteer there? You guys 1 or you 2? Okay.
y bar minus covariance of x and y divided by variance of x, and that's multiplied by s bar?
Yes, that's right. So which of the different potential routes did you guys take to doing that or defining it?
It's a linear equation, so we know the slope of it. So all I need to do is find a point at that line and intersect that x bar and y bar.
Right. So that's absolutely true. So that if you've taken econometrics, for example, you might remember that the regression line goes through the mean of the data, which is x bar and y bar. So once you know that, then, for example, you can just write y bar is equal to alpha plus beta x bar, and you're basically done at that point after you substitute in the covariance of x and y for the variance of, or the covariance of x and y divided by the variance of x for beta. So you get alpha is equal to y bar minus beta x bar, and then substitute in for beta. Also, if you weren't sure that the regression line went through the mean, I basically told you that it went through the mean with a hint. So e bar is equal to 0. So what you could think of doing, since this is a linear function, you could basically apply the mean operator to it. So do the sum 1 over n times the sum of y is going to be equal to 1 over n times the sum of alpha plus beta x plus e. But then since it's a linear function, you know that the summation can go through here. And so what you end up with is essentially, so this is y bar. It's going to equal the sum of alphas n times 1 over n. So that's just going to cancel out and become alpha. So you're going to have n alphas summed up there. Then it'll be beta times the sum of x divided by n, which is just beta times x bar. And then you're going to have the sum of the e's times 1 over n, which is just e bar. And I told you that that was equal to 0. And then the other way that you could have gotten there, if you had wanted to kind of go down like the calculus route, would be to take this function here, differentiate it with respect to alpha, and differentiate it with respect to beta. In particular, if you differentiate it with respect to alpha, that'll very quickly get you to the point at which you want to be. So if you take this guy and you differentiate him with respect to alpha, what you're going to get is so say that function is like f. So the derivative of that thing, which we'll call f, with respect to alpha is going to be equal to the sum from I equals 1 to n of 2 times yi minus alpha minus beta xi, and then times the times the derivative of the inside with respect to alpha, but that's just going to be equal to minus 1. So that's the derivative, and then of course you set it equal to 0. You can multiply through by minus 1 just to not have that thing running around, and might as well divide through by 2 also to make it easier. And then basically you're there. So this, you have the sum of the y's, you have minus the sum of the alphas, and then you have minus the sum of beta x, and that's all equal to 0. So this is the sum of n alphas is just equal to n alpha, so we can substitute that there. And then basically at that point you really are done. So you would just divide through by n to get alpha by itself, add it to the other side, and you'd have alpha is equal to 1 over n, the sum of y minus beta times 1 over n times the sum of x. And of course this is just y bar here, this is x bar there, and then we can substitute in the covariance and variance for beta. Right. Right. Yeah. So there's plenty of ways to do it, and the end result is that when we do a linear regression, we're going to get we're going to get two things. One is we're going to get a solution for beta, which is given by this formula, and then we're going to get a solution for alpha, which would be given by wherever I wrote it up here, over there. Let me just substitute in as well. So if you basically just have like a few summary statistics from the data, you can actually get this regression line. All you need are the means of the two variables, the covariance, and then the variance of x. Okay, and I want to emphasize that like this relationship is always true. So it's always the case that the regression line or the regression coefficient is going to be equal to the covariance between the two variables divided by the variance of x. How you interpret that resulting coefficient, whether you give it a causal interpretation or whether you say it's just kind of describing what we call like a descriptive relationship, is going to depend on a number of factors, but most importantly, it really depends on how you think the variation in x arose, like whether you think it's basically the case that x is being randomly assigned or at least is varying in a way that's unrelated to other determinants of the outcome y, or whether or not you think it's correlated with things that determine y. So sort of in the context of this equation, we worry about whether xi is correlated with this term ei, which is supposed to represent all of the other things that determine y that we don't observe. Now, all of this was derived under the assumption that this conditional expectation function was in fact a linear function of x. That doesn't have to be true. So in the example that we plotted earlier, it doesn't seem like, so if we look at this red line, I think that it's sort of representing the true conditional expectation function. It doesn't look like that's really linear, although that's somewhat deceptive again because, as I said, out here it's really being just influenced by a single observation. I forget, I generated this data like a year or two ago, but I would be surprised if it were not the case that I actually generated it using a linear function. So I think the true underlying conditional expectation function here is in fact linear, and that red line is just a little bit deceptive because of the outliers. But there could be true cases in which it's nonlinear. And in the case where that red line is in fact representing the correct conditional expectation function and is a nonlinear function, it turns out that regression still provides what we call the best linear approximation to the nonlinear conditional expectation function. So in practical terms, what that means is the regression is going to give the straight line that most closely fits the potentially curved conditional expectation function. That's probably going to be good enough for most purposes unless your CEF looks really weird. So if that red line actually represents the true conditional expectation function, it just bounces all over the place going up and down, then trying to sort of approximate it with a linear straight line is not going to work very well, but in most cases it'll probably work fine. So just to conclude here, it's always safe to apply what I'll call a descriptive interpretation to the regression coefficient. So the regression is going to summarize the conditional expectation function. It'll always be safe to say, look, I ran this regression, I got this coefficient, the slope coefficient beta, and I'm going to interpret it by saying that if we observe that x increases by 1 unit in our sample, then on average we expect y to increase by beta units. So in our specific example with air pollution hospitalizations, we're saying if we observe air pollution falling by 1 part per million or 1 unit in our data, then we expect daily hospitalizations to fall by beta, whatever beta happens to come out to be in the regression estimate. But that doesn't imply that beta represents the causal effect of reducing daily air pollution. So for example, it wouldn't necessarily give you the effect of some sort of pollution tax or something that would reduce air pollution. It would not give you the effect of that tax on hospitalizations. And the reason is that, as you probably know, even without taking econometrics, correlation doesn't imply causation. So the next lecture will basically talk more about causality and when we can ascribe a causal interpretation to a regression coefficient versus when we just say it's sort of describing a relationship in the data.